wave optics. So in this chapter, okay, we have to study about optics and related about its wave mechanics. So first of all, we will see its introduction. Okay. So in earlier standards, we have learned that light travels in a straight line while traveling through a uniform and homogeneous medium. The path of light is called a ray of light. On encountering an interface with another medium, a ray of light gets reflected or refracted, changes its direction, and moves along another straight line. The reflection is such that incident ray, the reflected ray, and normal to the boundary surface at the point of incidence are same plane, and the angle of incidence, that is the angle between the incident ray and the normal to the reflecting surface, is equal to the angle of reflection, that is angle between reflected ray and the normal for refraction of light while traveling from medium 1 to medium 2. The laws are: first, the incident ray, refracted ray, and normal to the boundary between two media at the point of incidence are in the same plane. And second, that is the angle of incident I, angle of refraction R, are related by N1 sin I is equal to the N2 sin R. So where N1 and N2 are the absolute refractive indices of medium 1 and medium 2 respectively. We have also learnt about the reflection of light produced by spherical mirrors and refraction of light through prisms and curved surfaces of lenses. So the position and nature of images, that is whether real or virtual, depend on the position of object and the focal length of mirrors or lens. Now on the basis of this basic explanation, we have to study nature of light. So first of all, we will consider that is corpuscular nature. The formation of shadows as well as images by mirrors and lenses has been understood by considering rectilinear motion of light rays. This fact led R. Descartes to propose a particle nature of light in year 1636. Then Newton developed this concept further and proposed that light is made up of particles, that is corpuscles, which are hard, elastic, and massless. A source of light emits these corpuscles which travel along straight line in absence of any external force. Then, when the light corpuscles strike a reflecting surface, they may undergo elastic collision, and a result follows the laws of reflection. So during refraction, it is the difference in the attractive force between the corpuscle and the particles of medium that causes a change in direction of the corpuscles. So, a denser medium exerts a larger attractive force on light corpuscles to accelerate them along the normal to the boundary. So, Newton's theory predicted that speed of light in denser medium would be higher than that of in rarer medium, but this contradicts the experimental observation. So in this theory, light of different colors correspond to corpuscles of different sizes. Newton performed several experiments in optics and could explain their result based on his theory. The study of optical phenomena under the assumption that it travels in a straight line as a ray is called ray optics or geometrical optics, as geometry is used in this study. So, the laws of reflection and refraction and the formation of images that we studied in earlier standards fall under this category. So, that we will see its basic phenomena, okay, about this theory, that is wave nature. So, to circumvent the difficulties in corpuscular theory, It was proposed by the Dutch physicist Higgins in the year 1668 that light is a wave. Higgins assumed light to be a wave caused by vibration of particles of medium, as light could also travel in vacuum. He assumed that a hypothetical medium called ether is present everywhere, including in vacuum. Note that this ether is not a substance, ether gas. Consider that is ether gas that we come across in chemistry. There was, however, no evidence to prove its existence, and thus it was difficult to accept this concept. So, in the 19th century, certain new phenomena of light, namely interference, diffraction, and polarization, were discovered. This could not be explained based on corpuscular theory and needed wave theory for their explanation. So, Huygens theory could not only explain the phenomenon but could also explain the laws of reflection and refraction, as well as the formation of images by mirrors and lenses. So, it was then accepted as the correct theory of light. Wave theory show that if the speed of light wave in denser medium is smaller than that in rarer medium, then light bends towards normal. So we know this all concepts. So wave nature of light could explain all the visual effects exhibited by light. The branch of optics which uses wave nature of light to explain the optical phenomena is called wave optics. Now, in this chapter, we are going to study wave optics and learn how the laws of reflection and refraction can be explained, assuming the wave nature of light. We will also learn about the phenomenon of interference, diffraction, and polarization and their explanation based on wave optics. The reason why geometrical optics work in case of formation of shadow, reflection and refraction is that the wavelength of light is much smaller than the refracting surfaces, as well as the shadow causing objects. So we will see that one encounters in laboratory or in day-to-day life. In 11th standard, we have learned Maxwell's equation, which suggests that light is an electromagnetic wave, as all waves known till Maxwell time needed a medium to propagate. Maxwell invoked the all-pervading hypothetical medium ether, the existence of radio waves and their speed being same as of that of visible light were experimentally verified by Hertz, that scientist H. Hertz. Later in 19th century, Michelson and Morley performed several experiments to detect ether but obtained negative results. The hypothesized ether was never detected, and its existence and necessity was ruled out by Albert Einstein when he proposed the special theory of relativity in year 1905 based on revolutionary concept of consistency of velocity of light. So this is the phenomenon about wave nature of light. Now we have to study dual nature of light. So in the early 20th century, it was accepted that light has dual nature. It can exhibit particle nature as well as wave nature under the different situation. Particles of light are called phonon, and we learn about more about it. So we know that when we consider particles, then we call it as a phonons. So this light also exert a pressure on our body. Okay, so which we can say when we close our eyes, okay, and when we turn on the light, then light will exert pressure on upper surface of our eyes. So we will see its theory now. Light as a wave. Light is an electromagnetic wave. These waves are transverse in nature and consist of tiny oscillating electric and magnetic fields which are perpendicular to each other and to the direction of propagation of wave. These waves do not require any material medium for propagation and can even travel through vacuum. So the speed of light in a material medium V depends on refractive index of medium N, which in turn depends on permeability and permittivity of medium. So we know that permeability means ability of medium to store magnetic field and permittivity means ability of medium to pass electric field. Then refractive index is equal to the ratio of speed of light in vacuum C to the speed of light in medium V. The refractive index of vacuum is 1, that of air can be approximated to be 1. So by using electromagnetic waves we can prove it. Electromagnetic waves can have wavelengths ranging from very small or smaller than a femtometer, that is 10 to the power minus 15 meter, to very large, larger than a kilometer. In the order of increasing wavelength, the waves are classified as gamma rays, X-rays, ultraviolet, visible, infrared, microwave and radio waves. So visible light comprises of wavelength in the range of 400 nanometer range. Waves of different wavelengths in the visible ranges are perceived by our eyes as different colors, with violet having shortest and red having longest wavelength. White light is a mixture of waves of different wavelengths. The refractive index of medium depends on the wavelength used. Because of this, for the same angle of incidence, the angle of refraction is different for different colors. Then except for normal incidence, and therefore the colors present in the white light get separated on passing through a transparent medium. This is the reason for formation of a spectrum and of a rainbow. So all this part we have studied in previous class. Now we will move about its theory, that is Higgins wave theory. Primary and secondary sources of light. We see several sources of light around us. Example, the sun, the moon, stars, light bulb, etc. These can be classified into primary and secondary sources of light. Primary sources are sources that light emit their own because first their high temperature, examples, the sun, the stars, object heated to high temperature, flame of any kind, etc. The effect of current being passed through them, example, tube of light, TV, that is television. And third, chemical or nuclear reactions. If you consider this part, that is nuclear reaction, examples, firecrackers, nuclear energy generators, light originates in these sources. And secondary sources are those sources which do not produce light of their own but receive light from some other sources and either reflect or scatter it around. Example include the moon, the planet, objects like humans, animals, plants, etc., which we see due to reflected light. Majority of sources that we see in our daily life, secondary sources, most secondary sources are extended sources, as can be seen from examples above. So first we will see about wavefront, okay, wavefront, and we will see again after that part, that is wave normals also we will see, okay. So first we will see about its wavefront. Now we have seen that when we drop a stone in water, surface waves commonly known as ripples are generated which travel outwards from the point, say O, where the stone touches the water. Water particles along the path of the wave move up and down perpendicular to the water surface. The path of wave at a point is defined by the state of motion of particle at that point as well as the distance of the point from the source. So in the next chapter we are going to in next chapter of 11th standard, okay, you can see it. So two particles are in phase, that is have the same phase if their state of motion is same, that is if they have same velocity and displacement but perpendicular to the water surface if they are the same distance from the source. As the waves are traveling symmetrically in all directions along the water surface, all particles along the circumference of a circle with center at O will have the same phase. The locus of all points having the same phase at a given instant of time is called wavefront. Thus, a wavefront is the locus of all points where waves starting simultaneously from O reaches at a given instant of time. In case of water, waves of water, the wavefronts are circles centered as O. The direction of propagation of the wave is the perpendicular to the wavefronts. That is along the radii of the circle. The speed with which wavefronts move is the speed of the wave. So water waves are two-dimensional waves. Now next, three-dimensional waves like sound waves produced by a source of light, a source of sound. Waves produced by a light source travel in all directions away from the source and propagate in three dimensions. Such a wave is called a spherical wave. In these cases, the wavefronts are surfaces passing through all points having the same distance from the source and having the same phase. Thus, in these cases, they are spheres centered on the source, say at O. The cross section of which are shown in figure 7.1. The spheres cross section of which are seen as circles in figure. Okay, so you can see this figure. Wavefront with the source at their center. The arrow are perpendicular to the spherical surfaces and they show the direction of propagation of waves. These arrows are rays of light that we have considered in earlier study of optics. So the wavefront shown in figure correspond to diverging of beams of light. Now we can similarly have wavefronts corresponding to converging beam of light. Such wavefronts can be produced after passing through the lens. So here two figures, spherical wavefronts corresponding to diverging beam of light. These are spherical wavefront, and below that this is nothing but plane wavefront corresponding to parallel beam of light. These are the plane waves. Now let us consider a spherical wavefront which have traveled a large distance away from the source. If we take a small portion of this wavefront, it will appear to be a plane, just like the surface of earth around appears to be a flat to around us, with the direction of propagation perpendicular to it. In such a case, the wave is called a plane wave. The wavefronts for a plane wave are shown in figure 7.1b. Okay, so if you want to see, you can see this second figure, okay, where arrows, that is rays, which are now parallel corresponding to a parallel beam of light, show the direction of propagation of wave. If the source of light is linear, that is along a line, the wavefront will be cylindrical. So there are three types of wavefronts available: plane wavefront, spherical wavefront and cylindrical wavefront. These three wavefronts are available. Fine, thank you.